Okay, so welcome to Math 408, L functions and sphere packing, lecture 19. And so what we're going to do today is we're going to talk more about modular forms and try to really get a sense of the different perspectives that we want to do. So we want to talk a little bit about them, in particular how a lot of things come down to trying to choose a good coordinate system, a good basis to look at things. As a aside, I want to review something from linear algebra, or you might have first seen it in Algebra 1, Algebra 2, the equations of conics. So I don't think we've covered conics yet in this class, that is correct. So what is the equation of an ellipse?
X squared over a squared plus y squared over b squared equals 1.
Okay. So x over a squared plus y over b squared equals 1. So you have just discriminated amongst ellipses. That's fine. I discriminate amongst ellipses as well. What are you assuming when you give me this?
That the ellipse is oriented horizontally or vertically?
Yes. That the ellipse is aligned with the coordinate axes. You could have a more general ellipse that is not aligned. And so I could give you an ellipse like this. And so here is my x and y, but the natural axes are u and v. We can study the ellipse in either the uv coordinate system or in the xy coordinate system. This is a senior seminar. This is a chance to try to tie together things you have seen in different math classes. Have you ever covered the equation of the ellipse when it's not aligned with the coordinate axes? Is that a yes or a no?
I have.
You have, okay. Who covered that with you?
I believe you did.
Yeah, I was wondering if it was me. So it's worth just talking about this briefly. The whole idea of linear algebra essentially boils down to, or at least a large part of linear algebra boils down to, choose the right coordinate system for the problem. Is it easy to write down the equation of the ellipse in UV space? Absolutely. And so what we want to do is we want to transform from XY space to UV space, write down the equation, and then transform back. So we have some matrix Q, which takes XY to UV. So it writes a point in an XY coordinate system with a point in a UV coordinate system. What kind of matrix is Q going to be?
Rotation.
It's going to be a rotation. So R of theta is cosine theta, sine theta, sine theta, cosine theta. And I know this is wrong. I have to choose where I want to put the minus sign. So if I want to rotate by 90 degrees, I want a point on the x-axis to go to the y-axis. So when theta is 0, I would have a 1 over here, and I would have a 1 over here. So I want this to be the positive, and I want this to be the negative. And so now, if I do r theta of 1, 0, I get 0, 1. If I do r theta of 0, 1, I will get negative 1, 0. So this will be a counterclockwise rotation of 90 degrees. And so you give me any point in xy space, I can write it in terms of UV. Physicists and mathematicians sometimes have a difference of, are you rotating the point or are you rotating the coordinate axes? Doesn't really matter as long as you are just careful and write things down. So what we can do is, if I want to write the ellipse in matrix form, I could write this as 1 over a squared, 0, 0, 1 over b squared, xy, xy, and this would just be equal to 1. So similarly, I can do it in UV space. So maybe 1 over a squared, 1 over b squared, 0, 0, UV, UV, and that's equal to 1. And now all I have to do is, if I call this matrix lambda, I can write UV as Q XY. This is the transpose, so this will become XYQ transpose. And this is now how you would write the equation of an arbitrary ellipse. It makes sense. Convert it to a better basis, analyze it there, and then convert back. This is exactly what we're talking about with the maps, with the Mobius transformations, saying the upper half plane is equivalent to the unit disk. Study it in either place, it doesn't matter. Look at the automorphism group of either one, it doesn't matter. You can go back and forth between the two. This is a general theme. What does this remind you of from linear algebra? Yeah, the diagonalization, the spectral theorem. So the question is, which matrices can you diagonalize? And then, of course, instead of looking at a 1 over b squared, if we had a negative 1 over b squared, we would have a hyperbola. And you can try to piece everything together and try to come up with a good overall picture. Okay. So what I want to do now is I want to talk about the generation of SL2Z by the two matrices. So theorem, SL2Z is generated by T and S. And T is the translation. S, I think I was putting the negative 1 up there. Just check if I'm doing my notes. Yes. And then A, B, C, D acting on Z is AZ plus B over CZ plus D. Sometimes we want to be a little bit more careful because if I take the negative identity leaves Z untouched. And this is because we are going to have a cancellation. We would have negative 1 divided by negative 1, it just cancels. So sometimes instead of looking at SL2Z, we might look at SL2Z and mod out by plus or minus the identity. And basically say, look, the identity and the negative identity will be considered equivalent matrices because they have the same effect. Okay, so I want to prove that SL2Z is generated by T and S. That means we can have any word in T's or S's. So the first thing we should think about is, what are the inverses of T and S? So what is T inverse? So there's a couple of ways to calculate T inverse. One is it's a 2 by 2 matrix. You can use the formula. Or can you just tell me structurally what you think T inverse should be? So thoughts on T inverse?
It should be like, just the upper right should be -1.
Yeah.
It should be the same.
So if you look at what T does, because A and D are both 1 and C is 0, it's just Z plus B. So it just adds 1. So the inverse would be to subtract 1. What about S inverse? So is it the same as S? Well, S times S is 0, -1, 1, 0, 0, -1, 1, 0, -1, 0, 0, -1.
So it should be negative S instead?
So this is where we have to decide. Do we consider S and negative S the same? So if we're considering S and negative S the same, then we're fine.
But wouldn't they be different rotations? So
No.
They have the same effect on Z.
Oh, then they're the same.
Right, and so this is you know, how much of a point do you want to make? Do you want to consider S and S different? If I go like this, now it's okay. So if we look at them as just standard matrices, S is not equal to the inverse of S. They differ by a minus sign. But if we only care about acting on the upper half plane with these, S and negative S have the same effect. And this is why we often look at SL2Z modded out by the plus or minus 1. And this is often called PSL2Z. All right. So now we know what S inverse is, we know what T inverse is. Any thoughts about how to show that SL2Z is generated by S and T? Again, it's a nice result, but what I care more is the thought process about how we get here. And this is why I'm deliberately not giving you stuff to read in preparation for the class. I want to just have you think about how you would attack this. So how might we start? So what's your game plan? How do you want to prove, given A, B, C, D, and SL2Z or PSL2Z show, and we'll give this a name, we'll call it gamma, show gamma is a word in T, T inverse, and S. If you don't like this equivalence, what could you say S inverse is?
Negative S.
Okay, but instead of negative S, I want to write S inverse just in terms of S's.
I said S.
I'm sorry?
S cubed.
S cubed. So I could say S inverse is S cubed. And so if we do that, we see we never need to use any S inverses in our words. And then we don't have to worry about, are we modding out by the plus or minus 1? S cubed is S inverse. Great. So we only need T, T inverse, and S's. So any thoughts about how we would show that an arbitrary A, B, C, D can be written as a word like this? Okay. Looks like a differential equation. It would have been wonderful if that had any relevance, but this is one of the reasons why I don't like to use color, is it will be, okay. So what are your thoughts? What's our game plan? So we hope gamma is equal to, say, T to the N1, S to the M1, T to the N2, S to the M2, dot, 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 T to the NK, S to the MK. So we hope that there is some kind of expression like this, and we need to find it. All right, okay.
We can try to move it all over and say that we can multiply these by gamma and get the identity.
Great. So I was about to pull out a Rubik's Cube and try to say, what we want to do is we want to come up with a set of moves that brings the Rubik's Cube to the identity. And then once we have that, we then just write them in the reverse order, and that will be how we get from the identity to where we want. So our goal is, given any matrix, map it to the identity by a sequence of t's and s's. Okay, so if we want a sequence of t's and s's, what we should do is we should figure out what t and s does to it. So I'm going to now give an advantage to everybody in Zoom land. So I'm going to try to share my screen. Can you see the Mathematica Notebook? All right, so because this is being recorded, I don't know if this will work. I'll try to just focus on it like this. So you can see the Mathematica code. And so I just quoted an arbitrary matrix M, S, T, inverse of T, inverse, I'm sorry, the identity matrix. And I quoted a way to just print things out. And so this will just print the product of the matrices and what the result is. I have no idea if that will have recorded. And I'll put that on the board right now. Let me start the share. Okay. So what we want to do is look at what everything does. Now, how many choices are there for acting on, a gamma by a t? I could act on the left or the right, and I could act with either t or t inverse. So just to save some time, I recorded what all of them are. So 1, 1, 0, 1 on A, B, C, D is equal to A plus C, B plus D, C, and D. And then 1, negative 1, 0, 1, so that would be the T inverse on A, B, C, D, would be A minus C, B minus D, C, and D. So this is, T on the left, T inverse on the left. And then I have T on the right. So A, B, C, D, 1, 1, 0, 1. And that will be A plus B, C, D, I think. C plus D. And then I have A, B, C, D, T inverse on the right. And that will be A, C, negative A plus B, negative C plus D. And then two more. 0, negative 1, 1, 0. So that's S on the left. A, B, C, D is going to be negative C, negative D, A, B. And then A, B, C, D with 0, negative 1, 1, 0 on the right. That will be B, negative A, D, negative C. For the record, if I had to, I could multiply these matrices. I am just trying to minimize the chance of making a typo. Hopefully, I have not made a typo. Okay, so these are the 6 different operations we can do. And the goal is to take a matrix A and come up with a path that will bring it to the identity. And again, while this is a nice result, what I care more is the thought process of how to do this. There's 2 ways to go. One is we could choose a specific matrix and play the game and see if we can get it to work. And then from that, try to generalize. And if we're not sure, then we do maybe several different matrices. The first question, of course, is do we actually have matrices in SL2Z? Are there 2 by 2 integer matrices with determinant 1? So what's true about the determinant of a product? It's the product of the determinants. So if I take 2 matrices that are 2 by 2 with integer entries and determinant 1, and I multiply them, it stays determinant 1. So all of these words are clearly going to be matrices that have determinant 1 and integer entries. So we know that there's matrices. The question is it everything? So any thoughts about how we might want to start? There's several ways we can do the proof.
I'm not sure if there's a way to start, but something about this looks like the Euclidean algorithm.
It is very similar to the Euclidean algorithm. There was a debate, and I know this is being recorded, between Professors Garrity and Adams a few years ago on which is better, I believe the Euclidean algorithm, or I think the trefoil knot. It's okay if I don't really remember what position Professor Adams had, because clearly Professor Garrity with the Euclidean algorithm has the far more important algorithm than anything from knot theory. Incredible how many applications there are of the Euclidean algorithm. When you look at a lot of things in geometry to prove that your groups have certain properties. Another one is in cryptography. So when you're doing a problem like this, instead of doing an arbitrary matrix, maybe it would be good to specialize and do a special matrix first. And then if you can show that any matrix of this form works, then instead of trying to get an arbitrary matrix to the identity, you only have to get an arbitrary matrix to that form. Are there any forms that might be easy for you? Yes?
Put a 0 in probably the bottom left.
Yes. Imagine C equals 0. So gamma is A, B, 0, D. Can you be more specific? So as soon as we take C to be 0, yes.
Well, we know that AD equals 1.
Yeah, we know AD, the determinant is 1. So AD equals 1. So either they both are negative 1 or they're both positive 1.
And then we can use the, like, multiply by 1, negative 1, 0, 1.
Yep. So without loss of generality, it looks like this.
Yeah.
And this is just going to be to the bth power. So if we happen to be in the special case when C equals 0, we win. And in fact, there's going to be a generalization of SL2Z. It'll be looking at matrices where the C is 0 mod n. And these will often, and I'm not going to go into entirely, these are the congruent subgroups. And the reason is if I give you A, B, C, D, and your E, F, G, H, and C is congruent to G is congruent to 0 mod n, when you multiply matrices like this, you put a star for something you don't care about. I don't care about this, I don't care about this, I don't care about this. I only care about the lower left corner. Since C is a multiple of n, C times Z, that's going to be a multiple of n. G times D, that's going to be a multiple of n. So this is going to be congruent to 0 mod n. And so if you have two matrices of this form, their product is of this form. So again, we may not cover that too much now, but it's nice to know that there is a structure and that structure is preserved. The lower left corner is actually a really good corner to look at. So all we have to do is take an arbitrary matrix and move it into upper triangular form. And again, if A and D were both negative, it would be extremely similar. We would just have to deal with the fact that, well, we're modding out by negative the identity. And so if it was negative 1, B, 0, negative 1, that's equivalent to 1, negative B, 0, 1. Okay, so we're making progress. And so I want to keep those 6 matrices. Let's try to minimize the pink. Okay, I just want to keep those 6 matrices there so we can see what actions we have. And so what we want to do is we want to choose a matrix and then decide, do we want to multiply A, B, C, D on the left or on the right by it? So what are the thoughts? And the goal is, go from A, B, C, D somehow to alpha, beta, 0, delta. That's what we're trying to do. We want to somehow get C down to 0. Any thoughts? Yes.
Our last step is going to have to be one of the far right too, because it's the only one that changes C.
Okay, the far right?
Yes. Our last step will be one
Yes.
of those.
Good. So if you look at everything else, C, 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 and what we can do in the last one is we can move C with D, or we can move C with A. So if we could get A to 0 or D to 0, we win. Need to get upper left or lower right to 0, then use S on left or right. Okay. How could we get A to 0? Does anybody have a sense of what is the key idea that's going to eventually emerge? It's an idea that emerges in a lot of number theory problems.
Can't you eventually just get the Euclidean algorithm from like multiplying by t?
Okay, so if we multiply by t, are we doing it on the left or the right?
Oh, sorry, t minus 1
Okay, are we multiplying that on the left or the right?
on the left.
Okay, so what we can do is we can subtract off multiples of c from A. So if A is larger than C, we can make it until A is smaller than C. So does anybody see what is going to eventually emerge? What are we going to use?
The determinant one part, it's like
Well,
saying something.
there is the determinant one, but this is a method in mathematics.
Oh.
Fermat used it.
Descent.
It's the method of descent. We can't be doing this indefinitely because we start off with bounded finite numbers. And so as we do this, as we keep iterating, as long as we can show it gets smaller, then we iterate again and it gets smaller, then we iterate again and it gets smaller. Okay, so what we want to do is basically some kind of descent Euclidean algorithm, your marriage. And if we do T inverse on the left, we can assume that A is less than C. We've got to be careful about whether or not A and C have the same sign or if they have different signs. But if they have different signs, we can use T rather than T inverse. And so without loss of generality, can we assume C is positive? Yeah, if necessary, just multiply the whole matrix by negative I. So without loss of generality, C is positive. Apply T or T inverse repeatedly on left until the new A tilde, has 0 less than or equal to A tilde is less than C. And so we can keep applying either T or T inverse to keep shifting the upper left entry by C. And so since it's moving in steps of size c, eventually it has to land in the interval from 0 to c. If it happened to land on 0, we'd be done. If not, okay. So now we know A, B, C, D. We apply a bunch of t's, t or t inverse repeatedly on the left. And now we get, let's call it A1, B1, C, D1. Although, what do we know about D1? It's actually D. I mean, I could write it as D if I wanted, doesn't really matter. And now we know C is greater than 0, 0 less than or equal to A1 less than C. If A1 equals 0, we're done. So imagine A1 is not 0. What do we do?
That's on the left.
Yeah, which one do we use?
Left.
We do it on the left, yes. So now we apply S on the left, and now we will have negative C, negative D1, that's terrible, A1, B1. And now what do we do? Lather, rinse, repeat. It's the shampoo method of mathematics, right? We do the T or T inverse on the left, and eventually we'll now get to A1, and I'll call this D2, B2, I'll call this C1, C2, sorry, and A2. So C2 is actually A1, it's greater than 0. And now we know 0 less than or equal to A2 is less than C2. If A2 equals 0, we're done. And now we see why it was so valuable that we handled the special case of upper triangular matrices first. Because as soon as we hit an upper triangular matrix, we're done, we can bail. And now notice we've done this, and the value here is getting smaller and smaller and smaller. So basically this is a descent argument. Cannot do infinitely often. Eventually, and say A sub L will have to be 0. So we start off with C in the left. We then got A1 over here, which was less than C. C2 is A1, which is less than C. And that is equal to C2. So every 2 times we do this, we know that the entry over here got smaller. And so if A2 or A3 or A4 is never 0, then eventually C2 is getting smaller. Eventually C2 is going to become 1. And then once that's 1, then the A has to be less than or equal to 0, I'm sorry, greater than or equal to 0, and strictly less than 1, and we will be done. So this is the proof. So we have now shown how to write an arbitrary element. There's something that's particularly nice about this proof.
It's constructive.
It's constructive. In one of my favorite moments in my Williams history, I had a thesis student a few years ago who I gave a problem related to Fibonacci numbers. I had constructed a game involving Fibonacci numbers, and I wanted to know how to beat my daughter, and that was her thesis. And she was able to prove that unless you take the number n equals 2 as your input, any other n, player 2 has a winning strategy. But it was a non-constructive proof. And I actually pulled my daughter out of school to come to the thesis defense and play my thesis student live, and she was warned, if my daughter wins, you may not graduate. It was a non-constructive proof, so my daughter had a chance. And afterwards she realized, oh, I see what I did wrong. I go, yeah, but she passes now. What was nice is we actually had a prospective student that we met for coffee later in the day, and she beat him, and he decided not to come to Williams. So there's some dangers with this. But non-constructive proofs, if that's what you can do, fine. But if you can have a constructive proof, that's so much better. And this is constructive. This tells us how to find. Now the question is, could there be more than one way to represent our matrix? It's essentially asking, are there some kind of trivial relations? Can you have two different strings of moves that will get you to the same point? And I'll leave that as something for you to think about as to how unique is this? And this is where, when you talk about the group, if there are no other relations on the elements, should all the words be distinct? What would it mean for two words to be the same? Okay. So I'm going to erase all the different matrices now. We no longer need them. We know that every element of SL2Z can be so generated. And what is great about this is when we want to figure out now how an arbitrary matrix acts, we can represent that matrix as a string of S's and T's. I will risk asking this question. When you did either like the change of variable formula, multivariable calculus, almost surely not there, or maybe in some things in linear algebra, did you ever represent your matrix as a product of elementary row operations, column operations, and then see what the effect of each one of them? So I had a freshman class at Yale that people either loved or hated. It was a unified multivariable calculus, linear algebra, point set topology, and vector analysis into a unified year-long class. If you only took one semester, you were screwed because you didn't know all of any subject. But if you did it year-long, you actually got to see how math interacts, and you would develop some linear algebra, and then you would go back to multivariable calculus and say, I want to do the change of variable formula. I'm going to break something up into a bunch of products of matrices. And if I understand how each one acts, I then understand how things act in general. So we are looking for modular forms. And the big thing we want is f of gamma of z. So gamma will be in SL2z. Z will be in the upper half plane. We want this to be cz plus d to the 2k f of z, where k is an integer. Now, life would not be what we're used to if there was agreed upon notation on anything. And so you can call this a modular form of weight 2k, or you could call it a modular form of weight k. Is that k has to be even, so we often write it like this. This is not quite the full definition of modular form. I need some kind of growth rates, I need some kind of continuity and stuff like that, but I basically want something that transforms nicely. And the question is, why is this the one that we want? If you look at d of gamma of z over dz, look at how those infinitesimals change. I think it comes out in the numerator. You get cz plus d to the minus 2. And so if you've seen differential forms, if you have f of gamma of z, d of gamma of z to the k, that would be f of z dz to the k. If you haven't seen modular forms, don't worry about it. It's just saying these are a nice thing. We have a nice way of keeping track of how things change as we move through the upper half plane. And I've told you, -1, 1, 0. And if we go at about a half, essentially this is the fundamental domain. We have to be a little bit careful. We don't want to count any point twice. And so we remove a little bit like that. The first question I have is if I give you any point z, can you give me a string of t's and s's that will map it into the fundamental domain? So this isn't too bad. If z is high up, you just use some t's and translate it over. If you take the fundamental domain and you apply s, you come down here. So this would be s of the fundamental domain. So if we translate t and we come up either here or in here, we win. The only danger is if we come in one of those regions over here. But if you come in one of the regions over here and you apply s, what happens to you? You'll now be above the unit circle, right? And you can translate, but maybe you come up over here and you apply s again and you translate, maybe you come up over here. So there's a little bit of work that needs to be done. So as a nice exercise, try to do that little bit of work and show that given any z, you can map z into the fundamental domain. So let's make that homework. Show can map any z to the fundamental domain. All right. And then the next question, and I'll leave this for you to think about, is I have written down a desirable property. I want a function that's going to behave nicely under translations by SL2Z. Does any such function exist? There is one function you should be able to scream out at me right now. There is one f that has to work. If you are thinking too hard. There is a choice of f that will truly work.
The zero function?
The zero function, right? So we know the zero function works. So the question I want you to think about is, can you think of any process, any construction that would give you something that would be nice, that would have this kind of transformation? And so rather than writing down the answer, just think, can you find such an f? All right, so we've gone over in a few classes, so for this class we're going to stop just a little bit early.